Blue suit, red cape. The most iconic original hero on Earth is, of course, Superman. Created by Joe Shuster and Jerry Siegel, Superman debuted in American comics and was adapted into a science fiction film in 1978. The film became a global hit, ranking among the top titles in international box office charts of its era. While the story is a classic, the most controversial moment is the scene where Superman turns back time to save his lover. After losing Lois, he makes the Earth rotate in reverse. It's a cinematic device. The apparent reversal is presented from the perspective of a near-light-speed Superman. But even so, it sparked huge debate at the time. So setting the movie device aside, what if Earth's rotation really reversed? Inspired by this timeless scene, let's explore the scientific what if. In this episode, we'll examine what happens if Earth begins rotating in reverse. First, a brief primer on Earth's rotation. Earth spins like a top around its axis, which connects the North and South poles, and the axis is tilted about 23.4 degrees relative to the ecliptic plane. This tilt drives seasonal changes in sunlight. In summer, the sun appears higher. In winter, lower, with shorter days. Around the equator, Earth's rotational speed reaches about 1,600 kilometers per hour. Since typical airliners cruise at roughly 800 to 900 kilometers per hour, equatorial rotation is about twice that, and about 1.3 times the speed of sound, approximately 1,200 kilometers per hour. In addition, centrifugal force from rotation is strongest at the equator, subtly shaping sea level and the geoid. Now, what if we flipped only Earth's spin to reverse? Would everyone slam into walls at 1.3 times the speed of sound the instant rotation changed? No, not exactly. If the spin reversed, everything on the surface would continue moving in the same prior direction due to inertia. Inertia means that an object, absent external forces, keeps its current state of motion or rest. When a car or train brakes hard and you lurch forward, that's inertia. In reality, the surface, atmosphere, oceans, and subsurface each have different viscosities and coupling strengths. So, layer-by-layer response times would misalign, making failure patterns far more complex. If Earth's reversal happened extremely quickly, structures that seem solidly planted and deep-rooted trees alike would fail under the sudden velocity change. Humans, too, would face catastrophic impulses that could hurl them violently. On top of that, transport systems, power grids, and communications satellites would suffer wide-area outages because their design assumptions about direction and velocity fields would break. And what is the largest movable mass on Earth aside from the crust? Forests, cities, it's the oceans. Shake a glass of water and waves form. Stop it abruptly, and the water nearly spills. Scale that up to Earth's oceans, and you get unimaginable megatsunamis striking coasts, resculpting shorelines, deltas, tidal flats, and coral reefs over vast areas. With changes this abrupt, the terrain could collapse before we could even assess impacts. Furthermore, temporary mismatches among tides, inertia, and Coriolis force could trigger tidal resonances in some basins, amplifying wave heights beyond anything recorded. What if, instead, we reversed gradually over sufficient time to keep inertia manageable? Even then, rotation affects invisible layers crucial to life. Earth's magnetic field, geomagnetism. Geomagnetism is Earth's global magnetic shield. It acts as a barrier against cosmic rays, high-energy electromagnetic radiation, and charged particles, protecting life and electronics at the surface. Cosmic rays are potent. A single injected charged particle can upset integrated circuits aboard satellites. And solar wind, a stream of superheated charged particles from the sun, could strip the atmosphere without geomagnetic protection. As the field weakens, ozone chemistry becomes more fragile, and UV/X-ray flux at the surface would increase, raising biological risks. Earth's interior consists of a conductive solid inner core, mostly iron, and a surrounding liquid outer core. Driven by thermal and compositional gradients and by rotation, the outer core slowly circulates. Interaction between the conductive inner core and the moving outer core generates electric currents, and in turn, the magnetic field, the geodynamo. This mechanism is highly sensitive to spin direction, rate, and convection patterns. To reverse slowly, rotation must pass near zero angular velocity. During that passage, the field weakens or temporarily collapses, leaving Earth exposed to cosmic rays and solar wind. Depending on duration, even if humanity avoids immediate harm, ecosystems would almost certainly be hit hard. Expect mass loss in high-latitude biomes, light damage to marine phytoplankton, rapid shifts in crop belts, and food web cascades. What about a world with permanently reversed rotation? At the 2018 General Assembly of the European Geosciences Union, EGU, researchers presented simulations that not only flipped Earth's spin, but projected impacts thousands of years forward, including environmental and ecological changes. Key findings: mid-latitude westerlies, normally blowing west to east, would flip. Familiar pressure patterns would reorganize. Ocean current vectors would invert, restructuring warm and cold current systems. Consequences could include greening of deserts, desertification of tropical rainforests, and grassland expansion over present permafrost. In short, a global remapping of climate zones. With mean temperature distributions shifting and specific guilds, plants/animals booming or collapsing, ecosystem impacts would be extreme. On the human side, the felt order of seasons and the sense of the international dateline would change. Sea-land breezes and monsoon phases would invert, forcing deep redesigns of social infrastructure. There's more. Long-term processes, tides, lunar precession, and tidal friction, spin deceleration, must be reevaluated. Reversing spin alters the sign and magnitude of tidal friction, potentially changing the moon's recession rate and the long-term trend in day length. It could also perturb tectonic stress fields and mantle convection, redistributing volcanic and seismic activity over century to millennium timescales. In summary, a sudden reversal unleashes catastrophic mechanical damage, while a gradual reversal leads to geomagnetic collapse and circulation upheavals, driving long-term, planet-wide environmental change. Earth's spin direction is the baseline of our living system. Altering it could simultaneously hit the biosphere, technosphere, and climate system. The bottom line, reverse rotation is not a movie-style fix. In the real world, it's a trigger for compound disasters. That's all for Curiosity Science. See you next time.